All right, well, let's get started. Thanks everybody for joining. My name is Jason Edwards. I'm a staff engineer over at USAA. We're gonna have a little bit of fun here as we close out the Reactive Summit, talking about reactive architecture and distributed systems. If you're not familiar with USAA, we're a financial services provider focused on the United States military members and their families. A little bit of slideware there about that. So what we're going to cover today for a lot of y'all is going to seem like some really basic stuff for those of y'all who are reactive pros already. But there was a really good couple of questions in the previous session of how do we articulate the value of reactive and these complicated techie concepts to our business partners. And so that's absolutely my goal here, is to equip y'all with some hopefully easy to grasp analogies and visualizations of what we mean by reactive, some of the concepts of distributed systems that really our business needs to know about and make some decisions on, and then take a look at event sourcing and CQRS and why they are such powerful tools for us to use. And if nothing else, I hope to make you laugh because we are going to have some fun with it. So we've been spending this whole conference talking about reactive. And I don't know about you, but when I first started getting into reactive, I was a little bit confused about, well, we talk about reactive architecture and it seems to mean one thing, and we talk about reactive programming and it seems to be another thing. So we're going to spend a minute here just kind of doing some disambiguation. So reactive architecture, also called reactive systems, when you hear folks talking about the reactive manifesto, wanting to have responsive applications that are elastic and resilient and have an underpinning of being message driven, that's talking about reactive architecture or reactive systems. So reactive architecture is focused on how the overall components of your system interact with one another. It's not concerned with individual lines of code and low-level implementation. A reactive architecture means you need to really embrace distributed systems concepts. And so we'll get into that in a little bit of what that means, but eventual consistency is definitely one that comes to mind. And as far as elasticity, one thing I'll point out is that apps can be designed to kind of synergize that, make use of that with all of our cloud platforms and Kubernetes and stuff. It's easy to scale up more instances of our application. But if your application is designed such that, hey, everything ends up waiting on a lock in the database anyway, your application is not elastic, even though you can spin up 100 instances of your app. And I would say, kind of on that note, it has some suggestions about how you do your persistence. Event sourcing is obviously a very popular persistence paradigm for reactive applications, but you don't have to be doing event sourcing to have a reactive architecture. Just make sure that your persistence platform is horizontally scalable so you can kind of meet with that elastic tenant. So on the flip side, we talk about reactive programming. And a lot of times you'll hear that we're talking about the reactive streams specification, and you have publishers and subscribers and non-blocking asynchronous back pressure. Anyways, reactive programming is talking about specific APIs for describing a chain of operations. Usually you have some data being produced, it's getting transformed in some way and getting sent somewhere. And those operations are can be done on multiple different threads without waiting on each other. There's a lot of different implementations out there. Just for the JVM, you've got Spring's Project Reactor, you've got Akka Streams, you've got RxJava, you've got Eclipse's Vertex, there's others as well. And all those implementations, they can interact with each other if they comply with this reactive streams specification. So reactive streams is kind of like the glue that allows our reactive programming libraries to all play nicely with each other. One thing that I want to point out is just because you're doing reactive programming, just because you're using one of these neat little reactive libraries in your application, does not mean that you have built a reactive application or that you have an overall reactive system, reactive architecture. On the flip side, you can have a solid reactive system with good reactive architecture principles, and you don't have to write a single line of code of reactive programming. So the concepts are related, but they're not like joined at the hip. So to kind of visualize the difference here, here's a goofy little online shopping experience API, which involves calling down to an inventory microservice, a sales microservice, and then there's another microservice for doing invoices. And we're going to point out which things on this picture fall in the category of reactive architecture and which ones are reactive programming. So starting out here on the bottom left, our shopping experience API has a cache for the inventory data. So it tries to call the inventory API to see, do we have that thing in stock? But you know what? If the inventory API is down, we've got a local cache that we can use to say, yeah, we probably have that in stock. We'll let you go ahead and add it to your cart. When the shopping experience API is calling downstream, we're using some of our good microservices resiliency patterns like circuit breakers or retries and timeouts and bulkheads and all those fun things, because your downstream system may not be working right now. It may be slow, maybe broken, and you want to be resilient to failures in the downstream. Here where we're integrating with our invoice service, we're using Kafka to be able to send messages. That's right there at the foundation of the reactive architecture. Reactive manifesto is being message driven. And then up here on our inventory API, we're using event sourcing. I'd say event sourcing kind of blurs the line. It's a little bit of a reactive architecture thing, but it also affects the lines of code that you're writing. So I think it's also a little bit of reactive programming. And then finally over here, our invoice service is integrating up with our inventory API. So somebody pays their invoice and we decrement the inventory. We're using change data capture and again, using Kafka events to do that integration. So we got all these little reactive architecture things going on, but at the same time, we've got one little bit of reactive programming here with RxJava. We've got some akka going on up here in the inventory API. We're doing event sourcing, which as I said, kind of blurs the blinds a little bit. And then our sales API is using a Spring Boot with Webflux. So we got lots of reactive programming going on as part of our reactive architecture. But then we have this kind of an outlier down here. We've got a service that was built by a team, and you know what? They haven't seen the light of reactive. They're using a blocking servlet API. They didn't attend yesterday's awesome session about the Oracle R2DBC driver. So they're still using blocking JDBC. But you know what? Even though we have a totally non-reactive application here, our invoice service, it is part of an overall reactive architecture. Overall, the system is message-driven, it's elastic, it's resilient, and it provides a responsive experience for folks who are wanting to shop on our online store. So all that to say, you can have a reactive architecture without doing reactive programming. You can do reactive programming, but you still got to do your homework to have an overall reactive architecture. And so now we're going to lead into distributed systems. Bonus points, if you know what this is a picture of, go ahead and post it in the chat session here on the Hopin platform. So we're going to talk about a few things. We're going to talk about CAP theorem and how that relates to eventual consistency. We're going to talk about consensus, and we're going to talk about messaging patterns. So starting out with CAP theorem, let's just look at Alice and Bob. And Alice has got some pretty interesting data that she wants to keep. And so she's going to put it in this shiny silver cylinder here. I'm going to try hard not to call it a database. It's just a thing that she can put her data in. Bob wants to get some data out, so he goes and asks the shiny cylinder for some data, and everything is wonderful. And so this application that Alice and Bob are using has grown in popularity, and it suddenly is getting more and more traffic, and the shiny cylinder gets bigger and bigger and bigger and bigger until, you know what, that shiny cylinder is a little bit too big. So what do we always do? Well, when the shiny cylinder is too big, we split it into two pieces. We build a distributed system. We use a distributed database, or we use clustering, or what have you, to where we now have two shiny cylinders, and they need to talk to each other somehow to share data. But now what happens if Alice puts her data here in the shiny cylinder on the left, but something goes wrong and your shiny cylinders can't talk to each other? Somebody trips over a network cable, a router freezes up in your network, or whatever, something goes wrong. Well, what we call this here, where you have two shiny cylinders, both operating just fine, but not able to talk to each other, we call this a partition. Now, in light of a partition, Bob, when he wants to go get some data, we have a choice to make. Do we give Bob some data or do we not? It's a binary choice. We either give him data or we don't give him data. If we give him data, that data might be stale. It might be out of date, might not have the latest and greatest stuff that Alice put in on the left-hand shiny cylinder. Well, that's a choice for availability. We want to give Bob something, even if it's maybe out of date. Our other choice is, you know what? We really can't stand to give Bob any out-of-date data. We need data consistency. So Bob's request is going to fail because there's a partition. We can't guarantee that everything is up to date. And so we have the three ingredients here to CAP theorem. We have consistency, availability, and partition tolerance. You only get to pick two of those. And generally, when we're building systems where there's more than one server involved, it's really hard to say, I'm not going to pick partition tolerance, because you know what? Network cables get unplugged and all kinds of crazy things happen on your network. And when we choose availability, we're not throwing consistency totally out the window. Eventually, this partition is going to get resolved. These shiny cylinders are going to talk to each other, and the data will become, up to date. It'll become consistent. And so that's where we get this term eventually consistent. Because if we're choosing availability and partition tolerance, we're not saying we don't want consistency at all. We're just saying that eventually, if Bob asked the question again, we would get him a consistent view. Now, When we have applications that are deployed at a global scale, we're running in multiple data centers, multiple availability zones, you don't have necessarily just one choice of where you want to land on the CAP theorem spectrum. So here I have an example of an Oracle database in 2 data centers, and that Oracle database is set up with rack cluster to where you have 2 database server nodes talking to the same physical storage. Well, this, we can choose consistency and availability because it's very unlikely that these 2 nodes in a given data center are going to become partitioned from one another. They're like probably in the same rack with physically wired together. They're not likely to get partitioned from one another. But in between data centers, we can't really run a hard wire from one over to the other data center. We've got to go over unreliable networks in the internet and whatnot. So typically what we'll do is we will have some sort of technology that will replicate data. As changes are made on one side, it'll asynchronously get pushed over to the other side and vice versa. This is a choice for availability and partition tolerance. So all that to say, you can make different choices on the CAP theorem spectrum at different levels or scopes within your application. Everything that comes into a data center gets consistency, but you know what? Between data centers, we're going to rather choose availability. But what if Alice and Bob say, well, we really want consistency, even at the across data center kind of scope? Well, typically what we end up having to say is, you know what, Alice and Bob, y'all are both going to have to point over to this one data center here. We'll keep replicating to the other data center and have it as kind of like a hot standby. But you know what? If that data center goes down, you're going to have some availability issues until we can perform a failover. So that's CAP theorem and eventual consistency. And you've got some choices to make. Well, I say that, but actually your business has some choices to make. It's really not a technical decision. It's a business decision of what they'll allow. And then we get to, put on our technical hats and figure out how to accomplish what the business needs. So next we're going to talk about consensus. Usually this is explained with a thought experiment called the 2 generals problem. I'm going to have try to have a little bit more fun at it. Hopefully March of 2020 is far enough in our collective past that we can make a little bit of some jokes about it. If this example doesn't make sense, just go Google the 2 generals problem and you'll figure it out. So here we have 2 shoppers. It's March of 2020. There are supply chain issues, and that's not part of their vocabulary yet. And they're at the store trying to get the very last container of hand sanitizer and the very last set of TP in the whole store. And unfortunately, they were in such a rush to get to the store that they forgot to bring their cell phones. And now they need to coordinate who's going to go get what. Because if they don't divide and conquer, somebody else is going to go get the last one, and that's just going to be terrible for them. They forgot their cell phones, so they'll have an unreliable way of communicating with each other. They can throw a paper airplane across the store and really hope that the other person got the message. So shopper number 1 throws a paper airplane saying, okay, I'm going after the hand sanitizer. I need you to go get the TP, because if you come for the hand sanitizer, we're not going to get it. But I'm waiting for an acknowledgement. I say, okay, we need to hear back from shopper 2 to make sure that shopper 2 is in agreement with this plan. So shopper 2 sends a paper airplane back saying, I got your message. I'm good with the plan. Let's do it. So just to be sure, you're going to get the hand sanitizer, right? And that requires another paper airplane going back and forth and back and forth. And these 2 shoppers cannot guarantee that they both have come to the same decision. And so they spend so much time sending acknowledgements back and forth that somebody else gets the sanitizer and toilet paper. And that is just really too bad for our 2 shoppers. Well, what does this look like in technology? Well, here we have Alice, and she has some cool data, and she wants to put it in not 1, but 2 shiny cylinders. One of these might call itself a database. The other one might call itself a distributed commit log, which sounds cooler. But you know what? Other than the fact that we flip it sideways, it's still basically a database. But Alice says, you know what? I've got some data, and I want to put it in these shiny cylinders. So she sends a copy to both cylinders. And now she needs to make a decision. Am I going to commit the transaction, or am I going to roll back? And so we want these 2 shiny cylinders to both arrive at the same decision of, this is good data, we're going to keep it, we're going to commit, or you know what, something's wrong, we're going to roll this back. But unfortunately, these 2 shiny cylinders, they don't have a reliable way of communicating with each other. Their only way of communicating with each other is throwing a paper airplane by virtue of Alice saying, are you going to commit? Are you going to commit? Are you going to commit? Well, Alice is the one that's going to have to step in and say, you know what, we're going to commit. That's what we're going to do. But I forgot to tell you, there are dinosaurs in your data center, and they like to eat messages. This dinosaur might come in the form of a network cable getting yanked, or a power cycle on a server, or a switch, or a rack going out of commission, or whatever. There are dinosaurs, and they like to cause havoc for your applications. And so if you missed it, Alice was able to send the commit message to the cylinder on the left, but the dinosaur got the one on the right. And now our two cylinders have not made the same decision about whether to commit or whether not to. Before we kind of tile that all together into a real application, we need to talk about messaging patterns. When you've got Alice trying to talk to one of those shiny cylinders, or one of those shiny cylinders trying to talk to another, we have a couple of choices of how we're going to guarantee those messages get there. So let's imagine we've got three messages, A, B, and C, that some sender needs to send to a destination over on the right. We've got two wonderful little creatures that are willing to help us out. We have this rabbit up here that is very fast and very happy to help deliver our messages. But sometimes the rabbit gets hungry and that green envelope looks like some lettuce, and so the rabbit eats it. Well, we've gotten some of our messages there, but sometimes we drop messages, and that's just how it goes with the rabbit. The elephant is not quite as fast as the rabbit, but in case you haven't heard, elephants never forget. And so in the process of sending messages, if there's any confusion, did this green message get there or not, the elephant remembers, oh, I know what that green message was, and the elephant goes ahead and just sends another copy. Well, we call these at most once delivery. Your messages get there, except sometimes they don't. And at least once delivery. Your messages definitely get there. Sometimes they really get there, like multiple times. I don't know about you, but most of the time when I'm talking to my business partners about building an application, my business partner's requirement doesn't say, I want you to build an application that loses data, or I want you to build an application that makes extra work for me. They don't want a rabbit and they don't want an elephant. They want a unicorn, of course. And they want this unicorn to be able to take our pieces of information, send them to the destination without losing any and without duplicating any. They want the mythical unicorn of exactly once delivery. I don't know about you, but I've had a really hard time finding unicorns out in the wild that are willing to help me out. They're out there, but they're super rare. So usually in technology, when our business says they want exactly once delivery of messages from one place to another, instead of a unicorn, we get our trusty friend, the elephant, but he's got a buddy over on the receiving side, another elephant, who remembers, you know what, I've already seen this green message before, so I'm going to go ahead and squish this extra one, peace on out of here, and we are able to simulate exactly once delivery by combining at least once delivery with this concept of idempotence, or you might just call it deduplication. We make it so that, yeah, duplicates might get sent, but we take care of it on the receiving side to where it doesn't cause duplicate work. So now that we've learned about messaging patterns, here we have Alice again. She's wanting to put some data in her database, and she's wanting to also put some data into, let's say, a Kafka topic. I see this all the time. You have a legacy application, or you have an existing application that has an API rights to a database, and your business says, we want events because we want an audit trail, or we want to do reporting, or we want to do integrations with other systems. So go update this application to do events. And Alice decides that what she's going to do is, because this one over on the left is the real database, even though distributed commit log sounds cooler, she's going to send her data first to the, quote, real database, whatever that means. And then once that has been finished, she's going to send her data over to, oh, man, well, that's too bad. The dinosaur this time went and attacked Alice, and not only is the message gone, but Alice has lost track of what the message even was. She has achieved at most once delivery by sprinkling some code into her application to publish events after writing to the database. I say at most once because when the dinosaurs in the data center attack, sometimes we drop messages. It's in the database, didn't make it to our event topic, and that's too bad. Bob says, I don't want to drop events. I don't want that at most once delivery. I want a unicorn of exactly once. So Bob thinks he's clever. Before writing to the database, he's first going to publish his event over here to this shiny cylinder on the right. And then, oh, well, here comes the dinosaur again. Well, now we have a different kind of problem. We got exactly one copy of the message onto our shiny cylinder on the right, let's say our event topic, but it didn't happen over here on the left. So what I'd like to call this is we have a phantom event or a ghost event. We say that something happened in our system, but over here in the system of record, our database, our kind of main thing, we don't have that same thing having happened. And remember, this one over here is the one we're calling the real database. And it really doesn't matter which one we put horizontal or vertical, it works the same. So now Alice and Bob decide they're going to work together. We're going to solve this problem for our business. What we're going to do is we're going to have Alice first write her piece of data over here to the shiny cylinder on the left. And then if a dinosaur attacks, that's really unfortunate for Alice, but it's okay for the data. The data has been persisted. Bob's responsibility is to watch that shiny cylinder on the left for new things that have happened, and then send a copy of them to the shiny cylinder on the right. And if the dinosaurs come and attack before he's able to get a message replicated over, Bob busts out his dinosaur spray, get that dinosaur out of here, and well, I'm not really sure, did the message make it over there or did it not? You know, maybe there was a timeout or server crashed and restarted or whatever, but that's okay. The event is still over there on the left. Bob can just grab another copy, send it over to the right, and now we have our data in both places. We have achieved what we want with at least once delivery. Maybe Bob sends 2 copies over there, but at least one time we're guaranteed that it's there. And like I said, it really doesn't matter which way the shiny cylinders are. So if you want to write to your event topic first and then replicate to your database, totally fine. But the same kind of principle applies, that if you try to have either Alice or Bob directly writing to both, you're going to have a hard time when the dinosaurs strike. So how do we make life easy for Bob when he is watching things in the database and trying to replicate them to some other place? Event sourcing actually makes the structure of the database very easy for Bob to be able to follow, and also has some wonderful other properties that we've talked about in some of the other sessions here over the last 2 days. So in case you haven't picked up on it, this is some of the terminology in event sourcing. You have commands that get sent to an aggregate root in domain-driven design terms, or a persistent entity. When those commands come in, the entity will read from its current in-memory state to decide what to do with that command. It decides we're going to generate some events to record what happened. Those events get stored in a journal, typically some sort of database. And then once the events have been persisted in the journal, they are durable, they're committed, they're safe, then and only then do we update our state to reflect that the events have happened. And then we have these special kinds of commands that are called queries. They're just commands that don't generate events. They just want to read something about the data. So what does that look like in practice? If you've been mystified about how does an event sourcing application actually work, what does it actually look like? Over on the left, we've got a kind of traditional CRUD application. So this guy wants to withdraw $400 from his bank account. Our business logic says, well, first, let's see if he's got enough money in the account. So we get the balance with a select query. We say, okay, we've got 500 in the account, we're withdrawing 400, so we're going to update the balance to 100. We do an update query, and then we overwrite that row in the database for account number ABC with the new balance, and we have a new update time. This is a little bit challenging. You remember Alice and Bob working together to keep our 2 shiny cylinders in date. This is a little challenging for Bob because he's able to see in the database what the current state is, but he doesn't necessarily have insight into how we got there. He just sees that now the balance is $100. I'm not sure why. Event sourcing makes this a little bit easier by saying, well, when the command comes in to withdraw $400, we're going to handle that command by running some piece of business logic, our behavior code. That business logic is going to ask for the balance from our in-memory state, seeing that it's 500. And then we're going to persist a new event saying that money has been withdrawn. What you'll notice here is that we still have the full history of the account was opened with 200, 300 was deposited, 400 was withdrawn. We don't have in the database actually written down what the current balance is. After the events have been persisted, then we go update our state to say, hey, can you handle the fact that this withdrawn has happened? And then we update our state with the current balance. So that's event sourcing in a nutshell, if you haven't had a chance to see what it actually looks like yet. Now, with event sourcing, we again have this question about strong consistency versus eventual consistency, and at what scope within our application are we going to draw that? So we've got 2 data centers geographically separated. Within each data center, we've got 2 availability zones, and within each availability zone, we've got a couple of instances of our application. So let's say we have a command come in to withdraw $400 from the account. Well, first, what's going to happen is that persistent entity is going to read from the journal, the opened event, and the deposited event to find out, okay, the current state is that we have a balance of 500. Now, while that's still happening, let's say we have another command to withdraw $300. If you've got some mechanism of routing that same command or that new command to the same node as the first command, you're probably in good luck because your framework that's doing event sourcing can probably make sure that those commands run one after another and they don't run concurrently. But what if you don't get that strong consistency because the command landed on some other node within the availability zone? Well, while that withdrawn event is being persisted, this other node replays the events and arrives at a state of 500. Is that okay for your application that you have 2 commands being processed concurrently in 2 places and they don't have the same view of the data? That's up to your business to decide. And maybe your business says, you know what, that's not okay. We need strong consistency at the level of an availability zone. Well, what if we don't have the mechanics to be able to route that command to be guaranteed to go to that availability zone? What if it comes over here? Do we need to grow the scope of our strong consistency to say it's across the entire data center? Does your event sourcing framework support doing that? What about if we need to be able to handle if the command comes into a totally separate data center? Do you really want strong consistency across both data centers? Are you willing to sacrifice availability to get that? I don't know. You may or may not don't know either. Your business hopefully knows. If you can help explain to them what is the decisions that they're making and what the trade-offs are. So the last thing is this kind of alphabet soup of CQRS, and I'm going to start out with a little bit of a quiz or a poll. Go ahead and post in the comments section of all these data platforms that I put up here on the screen, or the ones that I didn't. Which one's best? You're building a new application. What's the best data platform to use for that application? Well, hopefully y'all have all caught on that this is a bit of a trick question. The answer is it depends on what you're building and what your application does. So let's say that you're building an application that needs to be able to do super high throughput writes. I need to be able to insert new rows of data, and that's the main thing I need to be able to do. There's a lot of platforms that do that well. One of them is Cassandra. Well, what if I need to do streaming event processing? Kafka's good at that. What if I need to do full text search? Elastic's good at that. Batch analytics, Hadoop's great at that. Graph modeling, use a graph database. But I don't know about you, but I've always been taught you build your application, you need to build it in where all the data is in one system of record. You better be using third normal form so there's no duplication of data. Every piece of data lives in exactly one place and nowhere else. Well, that kind of limits you that you have to accept both the strengths and weaknesses of whatever data platform you choose. With CQRS, what we say is, tell you what, we're going to send commands to interact with one of these data platforms. So let's say we're using event sourcing and we're writing to Cassandra. So we have commands that rehydrate their state based off the events in Cassandra, and then that generates new events. And Alice and Bob working together, remember, Alice is writing her data to Cassandra. Bob is watching Cassandra for new events and replicating them to all of these other data platforms. And now we can run queries against these different data platforms for the things that they're good at, event streaming or full text search or graph relationship modeling or whatever. But so yeah, we send the different kinds of queries to the platforms that are good at those types of queries. The last thing to really be careful that your business understands, though, is that each of these other data platforms, your query or read side, are eventually consistent. So you have your commands, they get sent to your write side database or data platform. Those events are getting replicated to your read sides. Don't forget, make sure you do at least once delivery. You don't want to have any possibility of events getting dropped, and then your read sides don't, not only do they not have consistent data, they will never have consistent data because that event gets dropped. And if you want exactly once, just remember your basic unicorn algebra, elephant plus elephant equals unicorn. You can have exactly once if you just add some duplication. And the important thing here, these are eventually consistent. If you send a command and it writes to the right side, you will not necessarily see the effects of that reflected on the read side immediately. But your business partners come along and say, we really want strong consistency. We want to make sure that when things happen over here on the right side, that our read sides immediately reflect that. Well, here's kind of an analogy I'll give you for that. That's like your right side database saying, tell you what, come to the dark side, join me with two-phase commit and XA transaction protocol, and we will all build one distributed transaction. Most likely your data platform is going to say, you know what, I don't really support XA protocol, so I don't want to do that. If they do, you really might want to think about saying no anyway, because in case you have forgotten, there are dinosaurs roaming around your data center, and they're going to see one of these read side databases as a wonderful thing to go attack and cause to crash. And if you're using distributed transactions, that transaction can't commit if any of your read sides that are part of that transaction are down. So tell your business they really want eventual consistency because it will give them a much better availability. You don't have 4 possible points of failure here that can bring down your whole application. If they really push you for the strong consistency, all I got to say is make sure you got plenty of dinosaur spray, because there are going to be dinosaurs that come and attack your system and your application. With that, that's all I've got. So we'll take it over to Q&A. Let's see what we got here. Somebody got it right. It is an ignition distributor on that picture earlier. Nobody wanted to volunteer the best data platform. Nobody was saying that, you know, Microsoft Access is the best one. Man, it's too bad. Any questions? Looks like we got a couple of questions coming in. So one of them, how does data typically get from the write side to the read side? I'd say that typically whatever framework you're using to do your event sourcing, whether you're using, you know, Akka Persistence or Axon framework or something else, it's typically going to have a mechanism for doing CQRS, for kind of following the stream of events and propagating them to some other system. If not, you can roll your own, just have something that's periodically polling the right side database to say, is there anything new? Is there anything new? And that's typically why we see event sourcing used with CQRS, is because event sourcing makes it very easy for us to look for, is there new data? We just say, are there new events? If you're not using event sourcing, then depending on what database platform you're using, there may be something called change data capture, where you can do what you might call derivative event sourcing. You can basically watch the list of things that are happening, like this row was updated, this row was inserted, this row was deleted, and kind of reverse engineer that into business events. Another question is, how do you implement an idempotent receiver without remembering every message sent? That is, with finite memory. Well, so idempotence and deduplication are not exactly the same thing. It may be that the operation you're doing is inherently idempotent. So if I go into the conference platform here and I go update my profile and I change my first name to Jason and hit save, it doesn't matter how many times I hit save, the end result is that my name is going to be set to Jason. That is an inherently idempotent operation. If it's something like depositing money into a bank account, you know, I would certainly love for that to be handled not idempotently. And so, you know, it gets retried and I get more and more money in my account. But that's not how we want things to work. And so typically what you'll do is you'll have a message correlation ID or a command correlation ID so that you can kind of remember, I've seen this thing before and I've already processed it. If you have finite memory, you know, one thing you could do is just kind of put like an expiration time of this thing, this event, or this command can be processed up until such and such time, because that's how long I remember the things I've already seen. But then you get into what are you going to do if that time has passed? How are you going to kind of compensate for that? So it's definitely a hard problem. All right, I don't see any other questions, so I'm going to go ahead and drop off. Thank you all, and have a wonderful day or evening or night wherever you are.